The date is November 12, 1940. Inside a dimly lit conference room deep within the Air Ministry building in London, a young man stands before Britain's most powerful military commanders. His hands tremble slightly as he spreads reconnaissance photographs and technical diagrams across the mahogany table. The air is thick with cigar smoke and skepticism. "Gentlemen," he begins, his voice steadier than he feels, "in approximately 60 hours, the Luftwaffe will launch the most devastating aerial assault Britain has ever witnessed. They will strike with surgical precision in complete darkness. And unless we act immediately, thousands of civilians will die." The generals exchange glances. Some roll their eyes. This isn't the first time someone has predicted doom. But this young physicist, barely into his 30s, possesses knowledge that could alter the entire trajectory of the Second World War. His name is Dr. Reginald Victor Jones, and he has discovered something that Hitler's high command believed was absolutely undetectable. Has found the invisible weapons that were supposed to bring Britain to its knees. This is the story of how one man's obsession with an impossible technology exposed the Third Reich's most closely guarded secrets, saved countless lives, and pioneered an entirely new form of warfare that continues, shaping military strategy 8 decades later. This is the story of the scientist who could see the invisible. The autumn of 1939 brought an unusual kind of warfare to Europe. While ground forces clashed along the Maginot Line and naval vessels prowled the Atlantic, another battle was beginning in the electromagnetic spectrum. A battle fought with radio waves, encrypted messages, and scientific ingenuity, rather than bullets and bombs. Dr. Reginald Victor Jones had been recruited into British intelligence only weeks before war was officially declared. At 28 years old, he was remarkably young for such a position, but his credentials were impeccable. He had studied at Oxford under Professor Frederick Lindemann, one of Britain's most brilliant physicists, and had already made significant contributions to infrared detection technology. The Air Ministry needed someone who could think like a scientist while operating as an intelligence analyst. They needed someone who could look at fragments of technical information and reconstruct entire weapons systems in his mind. They needed someone who understood that modern warfare would increasingly be won or lost based on technological superiority. They needed Reginald Jones. His office was small, cluttered, and perpetually cold, despite the radiator that clanked and hissed in the corner. The walls were covered with maps, diagrams, and photographs. His desk overflowed with decoded German communications, technical reports from crashed aircraft, and intelligence summaries from agents across occupied Europe. Jones worked alone most nights, long after his colleagues had departed for their homes or the air raid shelters. He found that the quiet hours after midnight were when he could think most clearly, when he could see patterns that eluded him during the chaos of the normal workday. It was during one of these late-night sessions in early November that Jones encountered the message that would change everything. The intercept had come through the government code and cipher school at Bletchley Park, where teams of cryptographers were beginning to crack German military codes with increasing regularity. This particular message had been transmitted from Luftwaffe headquarters to bomber units stationed in northern France and Germany. Jones read it once, frowning, then again, more slowly, then a third time, his pulse beginning to quicken. The message referenced something called X-Gerät, literally X-device, in German. It contained technical terminology that seemed to describe a navigation system of some kind. There were references to Knickebein, which Jones knew meant crooked leg, and mentions of beam intersections, precise coordinates, and guidance protocols. Most intelligence analysts would have filed this away as interesting but not immediately actionable. After all, the Germans were known to use radio navigation aids. Several countries did. There was nothing inherently alarming about that, but Jones saw something others had missed. The precision being described in this message wasn't consistent with ordinary radio navigation. The coordinates were accurate to within yards, not miles. The targeting protocols suggested something far more sophisticated than simple directional beacons. Jones pulled out a notebook and began sketching diagrams. He calculated frequencies, estimated ranges, and worked through the physics of radio wave propagation. What he discovered made his blood run cold. If his interpretation was correct, the Germans hadn't just developed a radio navigation system. They had created a precision bombing guidance technology that could direct aircraft to specific targets with unprecedented accuracy, regardless of weather, darkness, or visibility. They had found a way to turn night bombing, previously an imprecise affair that relied heavily on luck and general area targeting, into a surgical strike capability. Jones sat back in his chair, the implications washing over him. Britain's entire defensive strategy was predicated on the assumption that German bombers couldn't accurately target specific installations in darkness or poor weather. British factories, military installations, and infrastructure were considered relatively safe at night because bombers simply couldn't see well enough to hit precise targets. If the Germans had solved this problem, if they could bomb with precision around the clock in any weather, then Britain's industrial capacity was suddenly and catastrophically vulnerable. But Jones faced an immediate problem. Nobody was going to believe him. The morning meeting started badly and deteriorated from there. Jones had requested an urgent conference with senior Air Ministry officials, emphasizing that he had discovered a critical threat to British security. He had been granted 30 minutes, which he knew wasn't nearly enough time to present his findings properly. But it would have to suffice. The conference room was intimidating. Around the long table sat Air Chief Marshal Sir Hugh Dowding, commander of RAF Fighter Command, Air Vice Marshal Trafford Lee Mallory, scientific advisor Professor A.V. Hill, and several senior intelligence officers whose names Jones had been given but immediately forgot in his nervousness. These were men accustomed to making life-and-death decisions affecting millions of people. They had limited time and unlimited demands on their attention. They did not appreciate having that time wasted on speculative theories from junior analysts. Jones began with the intercepts, reading selected passages and explaining the technical terminology. He could see attention already beginning to wander. These were military men, not physicists. Dense technical explanations weren't going to persuade them. He shifted tactics, moving to the blackboard mounted on the wall. With chalk, he quickly sketched a diagram showing Germany and Britain, with lines representing radio beams emanating from German territory. "Imagine," Jones said, forcing his voice to project confidence, "that the Germans have established powerful radio transmitters along the European coast. Each transmitter broadcasts not a general signal, but a narrow, focused beam, rather like a searchlight, but invisible and made of radio waves instead of light." He drew another line intersecting the first. Now imagine a second transmitter broadcasting a second beam. At the point where these two beams cross, you have a precise location marker visible to any aircraft equipped with the proper receiving equipment. Air Vice Marshal Lee Mallory interrupted. "Dr. Jones, radio waves don't work that way. They diffuse, they spread out. You can't create a narrow beam over hundreds of miles. The physics simply don't support it." Jones had anticipated this objection. "Actually, sir, with the correct antenna configuration and the proper frequency selection, it is entirely possible to create a highly directional radio beam. The Germans appear to have solved the engineering challenges involved." "Appear to have solved?" Professor Hill interjected. "Dr. Jones, do you have concrete evidence that this system actually exists and is operational?" This was the critical moment. Jones's evidence was fragmentary. Intercepts, technical manuals recovered from crashed aircraft, second-hand reports from interrogated prisoners. Nothing definitive. Nothing that would stand up to rigorous scientific scrutiny. But intelligence work wasn't about waiting for definitive proof. It was about recognizing patterns, making informed inferences and acting on incomplete information before it was too late. Jones presented his strongest piece of evidence, a German pilot who had been shot down over Scotland and subsequently interrogated at the prisoner of war facility in Cockfosters. During questioning, the pilot had mentioned training exercises involving beam flying techniques. The interrogator hadn't thought much of it at the time, but the comment had been noted in the report. When pressed for details, the pilot had become evasive, clearly realizing he had said too much, but it was enough to corroborate the technical intercepts Jones had analyzed. "Gentlemen," Jones said, meeting each man's eyes in turn, "I understand this seems improbable. I know the evidence is incomplete. But consider the consequences if I'm correct and we do nothing. The Germans could strike any target in Britain with precision, day or night, in any weather. Our factories, our ports, our command centers, all would be vulnerable. We would be fighting a war where the enemy could bomb us with impunity, while we struggled to even find their aircraft in the darkness." The room fell silent. Outside, London was preparing for another night of potential air raids. Air raid sirens, blackout curtains, and the constant anxiety of wondering when and where the next attack would come, these had become the rhythm of British life. Air Chief Marshal Dowding spoke for the first time. His voice was measured, calm, and carried the weight of a man who had seen too many good people die based on bad decisions. "Dr. Jones, you're asking us to divert significant resources, aircraft, equipment, personnel, to search for something that may not exist. Those resources are desperately needed elsewhere. If you're wrong, you could be compromising our defensive capabilities at a critical time." He paused, studying Jones carefully. "But if you're right, the implications are indeed catastrophic. You will have your resources, Dr. Jones, but understand that if this proves to be a wild goose chase, your career in intelligence will be remarkably short. Do I make myself clear?" Jones nodded. "Perfectly clear, sir. Then I suggest you begin immediately. Find these beams, Dr. Jones, or prove conclusively that they don't exist. Either way, I want answers within 1 week." As the meeting dispersed, Professor Hill pulled Jones aside. "Reginald," he said quietly, using Jones's first name for the first time, "I hope you're right about this, because if you're wrong, there are plenty of people in this building who will ensure you never work in government again." Jones managed a weak smile. "If I'm wrong, Professor, we'll all have bigger problems than my career prospects." Within 12 hours of receiving authorization, Jones had assembled a small team of specialists. There was Dr. Robert Cockburn, an electrical engineer with expertise in radio systems, Charles Frank, a physicist who had been Jones's assistant since the war began, and Flight Lieutenant Harold Jordan, an RAF pilot with technical training who would coordinate the aerial search missions. Their mission was unprecedented: find invisible radio beams crossing hundreds of miles of airspace, determine their characteristics and purpose, and develop countermeasures, all before the Germans could use these beams to devastating effect. The technical challenges were enormous. Radio waves are, by their nature, invisible and intangible. They leave no contrails, make no sound, and pass through physical objects without leaving a trace. Detecting them requires specialized equipment, and understanding them requires expertise that spans multiple scientific disciplines. Jones began by establishing what he called a beam theory working group. This small team would analyze every piece of intelligence related to German radio navigation, cross-referencing technical specifications, pilot reports, and intercepted communications to build a comprehensive picture of the system's capabilities. Simultaneously, Cockburn began modifying RAF aircraft to serve as flying radio laboratories. These aircraft would be equipped with sensitive receivers capable of detecting radio signals across a wide range of frequencies. They would fly systematic search patterns over Britain, looking for the telltale signatures of German navigation beams. The first flights began on November 18, 1940. A modified RAF. Anson aircraft took off from an airfield in Lincolnshire just after sunset, its interior crammed with radio equipment and two operators monitoring multiple receivers simultaneously. They found nothing. The second night's flight also yielded no results, nor did the third, fourth, or fifth. Jones's critics within the Air Ministry began circulating. The beam theory was being dismissed as the fantasy of an overeager young analyst who didn't understand operational realities. Resources were being wasted on a hunt for ghosts, while real German bombers were pounding British cities every night. The pressure on Jones was intense. He spent every waking hour analyzing data, refining search parameters, and trying to figure out what they were missing. Sleep became a luxury he couldn't afford. Food was something he consumed absently at his desk without tasting it. Charles Frank watched his colleague with growing concern. "Reggie," he said one evening, using the nickname Jones's friends employed, "you need to rest. You're going to collapse if you keep this up." Jones looked up from his calculations, his eyes red-rimmed and unfocused. "We're missing something, Charles. The Germans are using these beams. I know they are. But we're not finding them, which means either our search methodology is wrong, or we're looking in the wrong place, or at the wrong frequency, or—" He trailed off, staring at the equations covering his blackboard. Then, suddenly, his eyes widened. "Frequency," he muttered. "We've been assuming they're using shortwave frequencies because that's what makes sense for long-range transmission. But what if they're using medium wave? What if they've found a way to make medium wave beams work over long distances despite the theoretical limitations?" Frank considered this. That would be innovative, and it would explain why we haven't found anything. We've been searching the wrong part of the spectrum. Jones was already calculating. Medium wave, around 30 megahertz. That would require specific atmospheric conditions, but it's theoretically possible. We need to reconfigure the search parameters immediately. That night, the modified Anson flew again, this time with receivers tuned to medium-wave frequencies that the previous searches had ignored. The aircraft followed a flight path that took it north from Lincolnshire toward the Scottish border. At precisely 22:47 hours, one of the radio operators suddenly sat upright. "Signal," he announced. "Strong directional signal, bearing approximately 095 degrees. It's narrow, very narrow, and it's steady, not fluctuating like a broadcast transmission." The pilot, following standing instructions, turned the aircraft to follow the signal. As they flew, the operators noticed something remarkable. The signal remained strong and steady as long as they flew a specific heading, but weakened rapidly if they deviated even slightly to either side. It was exactly the behavior Jones had predicted for a directional beam. "Mark position," the pilot ordered. The navigator carefully noted their coordinates. They followed the beam for 20 minutes, tracking its path across the countryside. The beam maintained its characteristics throughout: narrow, steady, and highly directional. When the aircraft landed just after midnight, the radio operators rushed their recordings directly to Jones's office. By the time they arrived, word had already spread. Air Ministry officials, some still in their dressing gowns, gathered to hear the results. Jones played the recordings, showing the clear spike in signal strength along the beam path and the dramatic drop-off to either side. He plotted the beam's trajectory on a map, drawing a line that extended from the German coast across the North Sea and directly over industrial targets in northern England. The room was silent as the implications sank in. "Gentlemen," Jones said quietly, "the beams are real, and they're already operational." Air Chief Marshal Dowding studied the map for a long moment. "How many of these beams are there, Dr. Jones?" "We don't know yet, sir. But if they've established one, there are almost certainly more. We need to conduct a comprehensive survey immediately." Dowding nodded. "You have your authorization. Find them all, every single one, and then figure out how to stop them." Over the following week, modified aircraft flew dozens of missions, methodically mapping German navigation beams. What they discovered was sobering. A network of at least 12 distinct beams, each precisely aimed at critical British industrial and military targets. The beams covered aircraft factories in Coventry and Birmingham, shipyards in Belfast and Glasgow, munitions plants in the Midlands, and even military installations in London itself. The Germans had created an invisible grid system that allowed their bombers to navigate with precision to virtually any target in Britain. Jones presented his findings at another Air Ministry conference, this time with visual aids showing the beam network overlaid on a map of Britain. The evidence was now undeniable. This system, which German communications refer to as Knickebein, or crooked leg, represents a fundamental shift in bombing capability, Jones explained. A German bomber equipped with a simple radio receiver can fly along one of these beams directly to its target. There's no need for visual navigation, no need for clear weather, no need for experienced navigators. A relatively inexperienced pilot can now deliver bombs with accuracy that would have required years of training just months ago. "Can we jam these beams?" asked Lee Mallory. "We can," Jones replied. "But not with ordinary radio jamming. We need to be more subtle. If we simply blast noise at the same frequency, the Germans will know we've discovered their system, and they'll modify it or develop alternatives. Instead, I propose we create false beams, counterfeit signals that will confuse the German receivers without making it obvious that we're deliberately interfering." It was an audacious plan, not to block the German system but to deceive it, to make German pilots think they were following their beams accurately, when in fact they were being led astray. The invisible war had entered a new phase. Before Jones could devise effective countermeasures, he needed to understand exactly how the German beam system worked. This required piecing together information from multiple sources, like assembling a jigsaw puzzle when most of the pieces were missing, and you weren't entirely sure what the final picture was supposed to look like. The breakthrough came from an unexpected source: a Luftwaffe bomber that crashed in the English countryside after being damaged by anti-aircraft fire. The aircraft, a Heinkel He 111, had come down relatively intact in a field near Reading. The crew had survived and been taken into custody, but more importantly, the aircraft's radio equipment was largely undamaged. Jones and Cockburn drove out to examine the wreckage personally. They arrived to find the aircraft surrounded by military police and RAF technical officers who were in the process of cataloging the salvage. "We need to see the radio systems," Jones told the officer in charge, "immediately, before anything is moved or disturbed." The interior of the aircraft was cramped and smelled of aviation fuel and burnt electronics. Jones and Cockburn squeezed into the radio operator's position, examining the equipment by torchlight. What they found was simultaneously elegant and sophisticated. The Germans had installed a receiver system that was far more advanced than standard communication radios. There were 2 distinct receiver channels, multiple frequency selection options, and a visual display that showed the pilot directional information. Most telling was a specialized antenna system on the aircraft's exterior. The antenna wasn't designed for general reception. It was carefully configured to receive signals from specific directions with maximum sensitivity. "Look at this," Cockburn said, pointing to the visual display unit. "It's a left-right indicator. When the aircraft is perfectly aligned with the beam, both indicators show equal strength. If the aircraft drifts to the left indicator shows stronger. If it drifts right, the right indicator dominates." Jones nodded, sketching diagrams in his notebook. "So the pilot simply keeps the indicators balanced, and he knows he's flying along the beam. Simple, intuitive, and effective." But there was something else. Cockburn had noticed additional equipment that didn't seem to be part of the basic navigation system. This equipment was more complex, with multiple receivers and what appeared to be some kind of automatic timing mechanism. "This isn't just for navigation," Cockburn said slowly. "This is something else, something more sophisticated." Jones felt a chill of recognition. The intercepted messages that had started his entire investigation had mentioned not just nicobine, but also something called X-Juret, the X device. Could this be it? They carefully photographed every component, made detailed sketches, and arranged for the entire radio suite to be removed and transported to a laboratory for detailed analysis. Back in London, Jones assembled all the intelligence they had gathered about nicobane and what he now suspected was a second, more advanced system. The picture that emerged was disturbing. Nicobine, the system they had already detected and mapped, was apparently just the beginning. It was a relatively simple system, one beam for navigation, perhaps a second beam to mark the target location. It gave German bombers general guidance to target areas. But X-Juret was something else entirely. Based on the equipment they had recovered and communications they had intercepted, Jones began to suspect that X-Juret used multiple beams in a sequential arrangement that allowed automated bomb release at precisely calculated points. He worked through the mathematics. A bomber flying along a primary beam would cross a series of secondary beams at precise intervals. By measuring the time between beam crossings and knowing the aircraft's altitude, an automatic system could calculate ground speed and release bombs at exactly the right moment to hit a specific target. It was brilliant, terrifying, and sophisticated beyond anything Jones had expected. "If I'm right about this," Jones told his team during a late-night working session, "X-Juret doesn't just guide bombers to a general area. It allows them to hit specific buildings from thousands of feet in altitude, in complete darkness, with accuracy measured in tens of yards rather than miles." Charles Frank, who had been studying the captured equipment specifications, looked up. "Reggie, if they can actually do this, they could take out specific factories, specific bridges, specific command posts. They could systematically dismantle our industrial capacity one precision strike at a time." Jones nodded grimly. "Which is exactly why we need to stop it before they can fully deploy it." Understanding how to defeat the German beam systems required Jones to think like a German engineer. He needed to understand not just what the systems did, but why they were designed the way they were, what their limitations might be, and where vulnerabilities could be exploited. He began with fundamental physics. Radio waves are electromagnetic radiation, similar to visible light but with much longer wavelengths. Like light, radio waves travel in straight lines and can be focused and directed using appropriate antenna designs. Unlike light, radio waves can pass through clouds, fog, and darkness without significant attenuation, making them ideal for navigation in conditions where visual navigation is impossible. The challenge the German engineers had faced was creating beams narrow enough to provide useful directional guidance over distances of several hundred miles. Radio waves naturally tend to spread out as they travel, with the degree of spreading inversely related to the frequency of the wave. Higher frequencies spread less, but are also more susceptible to atmospheric absorption and interference. The Germans had apparently settled on medium wave frequencies around 30 to 33 MHz as an optimal compromise. At these frequencies, with carefully designed directional antennas, they could create beams that remained focused enough over the distances involved to provide useful guidance. But here's where the German engineers had shown real ingenuity. They hadn't tried to create perfectly uniform beams. Instead, they had encoded directional information within the beam structure itself. Jones worked out the system through a combination of mathematical analysis, study of the captured equipment, and creative insight. The Germans had split their beam into two overlapping sections. The left half of the beam was modulated to transmit Morse code dots, short pulses. The right half transmitted Morse code dashes, longer pulses. But here was the clever part. In the exact center of the beam, where the two halves overlapped perfectly, The dots and dashes interleaved to create a continuous tone. A German pilot flying along the beam would hear this continuous tone in his headphones. If his aircraft drifted to the left, he would begin to hear more dots than dashes. If he drifted right, more dashes than dots. To stay on course, he simply had to keep the tone continuous and steady. It was elegantly simple, requiring no complex equipment on the aircraft, just a radio receiver and headphones. Any pilot, regardless of experience level, could follow the beam. "This is actually beautiful engineering," Cockburn admitted grudgingly as they worked through the details. "It's simple, reliable, and effective. The Germans have really thought this through." Jones nodded, but he was already thinking several steps ahead. "Yes, but simplicity can also be a vulnerability. If we understand the system this thoroughly, we can exploit it." He began sketching countermeasure concepts. The obvious approach would be to simply jam the German beams with powerful transmitters broadcasting noise at the same frequency. But Jones rejected this immediately. "If we jam them crudely, they'll know we've discovered their system. They'll switch frequencies, modify their modulation schemes, or develop entirely new approaches. We'll be starting from scratch every time. Instead, we need to make them think their system is working when it isn't." This led to one of Jones's most creative insights: the concept of masking beacons. Rather than blocking German signals, British transmitters would broadcast their own beams on the same frequencies, carefully synchronized with the German timing. These counterfeit beams would overlay the German beams, but with slightly different directional characteristics. German pilot following what he thought was the guidance beam would actually be following a combination of the real German beam and the British counterfeit. The two would be close enough that the pilot wouldn't immediately recognize anything was wrong, but different enough that he would miss his target by several miles. From the German perspective, it would look like equipment malfunction or atmospheric interference, not deliberate jamming. "It's like fighting in fog," Jones explained to RAF officers who would be operating the countermeasure systems. "The Germans can still see their beams, but they're distorted just enough to lead them astray. And because they can still detect their signals, they won't immediately realize they're being deceived." The technical challenges of implementing this were substantial. British transmitters would need to be powerful enough to interfere with German beams, but subtle enough not to make the interference obvious. They would need to be precisely tuned to German frequencies, which could change without notice. And they would need to be positioned to cover all the major target areas the Germans might attack. But Jones was confident it could be done. The physics was sound. The engineering was challenging but achievable. All they needed was time. Time to build the transmitters. Time to position them properly. Time to train operators. Time that Britain might not have. The construction of Britain's beam countermeasure network happened with remarkable speed. Driven by the urgent knowledge that every day of delay meant more British cities vulnerable to precision German bombing. Jones worked with the BBC and General Post Office to identify suitable locations for transmitter installations. They needed sites that were geographically positioned to cover likely German attack routes, had reliable electrical power, could be secured and defended, and wouldn't interfere with existing British communication systems. Within 3 weeks, the first experimental Meacon station became operational near Dover. The term Meacon was short for Masking Beacon, ATD, fitting name for transmitters designed to deceive rather than communicate. The station consisted of sensitive receivers that could detect German navigation beams, signal processing equipment that could analyze and reproduce the beam characteristics, and powerful transmitters that could broadcast counterfeit beams, synchronized with the German originals. The operators were a mix of RAF radio specialists, civilian engineers, and university students with technical training. They worked around the clock in shifts, constantly monitoring German frequencies and adjusting British countermeasures to match German tactics. Jones personally oversaw the first operational test. Intelligence indicated that a small German bombing raid was planned against a munitions facility near Reading. Nike beams had been detected pointing toward the target. "Remember," Jones told the Meacon operators, "we're not trying to completely block their navigation. We're trying to make it unreliable. Our counterfeit beam should overlay their real beam, but with a slight angular offset. The German pilots should still detect a steady tone, but they'll be following a composite beam that will lead them a few miles off target." The operation began at dusk. German bombers took off from their bases in northern France, climbing to bombing altitude as they approached the English coast. Aboard the aircraft, pilots and radio operators tuned their receivers to the Nicobine frequency, hearing the familiar dot-dash pattern that indicated they were approaching the navigation beam. As the aircraft entered the beam, the pilots heard the continuous tone that meant they were properly aligned. They settled onto their bombing headings, following the invisible path toward their target. But unknown to the German crews, what they were hearing wasn't just the Nicobine beam. It was a carefully crafted combination of the German signal and the British counterfeit, creating a composite beam that diverged from the original by approximately 3 degrees. At 200 miles per hour over a distance of 80 miles, 3 degrees of error meant the aircraft would miss their target by nearly 5 miles. At the munitions facility, air raid sirens wailed and workers rushed to shelter. Anti-aircraft batteries prepared for action. Fighter aircraft scrambled from nearby airfields. And then, in a field 5 miles south of the facility, explosions erupted. German bombs fell in open countryside, destroying nothing but grass and trees. The munitions facility was untouched. In the Meacon control room, operators monitored the results through various intelligence channels. When confirmation came that the raid had missed its target, cheers erupted. Jones allowed himself a small smile, but cautioned his team. This was just the first test. The Germans will adjust their tactics. They'll recalibrate their equipment. They'll conduct troubleshooting. We need to stay ahead of them constantly. Over the following weeks, Meacon stations proliferated across southern England. By December 1940, nearly 20 stations were operational, covering all the major routes German bombers used to approach British targets. The results were dramatic. German bombing accuracy declined precipitously. Raids that should have devastated specific factories instead dropped bombs in fields and residential areas miles from their intended targets. The Luftwaffe's vaunted precision, bombing capability was being systematically undermined by an invisible defensive network that they didn't even know existed. Just as the Nicobine countermeasures were proving effective, Jones's fears about X-Jurat were confirmed. In late December 1940, intelligence intercepts indicated that a special Luftwaffe unit, Kampfgruppe 100, was preparing for operations using special navigation equipment. This unit had been held in reserve, conducting extensive training, but not participating in regular bombing missions. Jones immediately suspected this was the X-Jurat unit. If he was right, they were about to face a much more sophisticated threat than Nicobine. His suspicions were confirmed when a German bomber from Kampfgruppe 100 was shot down over the channel. The salvaged radio equipment was unlike anything they had encountered previously. It included multiple receivers operating on different frequencies, an automatic timing device, and a complex visual display system. Jones and Cockburn spent an entire night analyzing the equipment. As dawn broke, they had worked out the system's operating principles. X-Jurat used a main beam similar to Nicobine for general navigation, but it also employed 3 additional crossbeams at precise intervals before the target. When the aircraft crossed the first beam, the pilot was alerted to begin his final bombing run. When crossing the second beam, an automatic clock started. When crossing the third beam, the clock stopped. The system then calculated the aircraft's ground speed based on the time between the second and third beams and the known distance between them. Using this ground speed and the aircraft's altitude, it automatically computed the correct bomb, release point, and dropped the bombs without requiring any action from the pilot or bombardier. It was a mechanical computer designed for a single purpose, delivering bombs to a precise location, regardless of visibility or weather. This is frighteningly sophisticated, Cockburn said. It's not just guidance, it's automated targeting. And our Nicobine countermeasures won't work against it because it uses different frequencies and a completely different operational methodology. Jones stared at the equipment, his mind racing through possibilities. We need to find these beams immediately. X-Giret operates on higher frequencies than Nicobine, which means they'll have different propagation characteristics. We need to reconfigure our search aircraft and start looking in a different part of the radio spectrum. The search began that same day. Modified aircraft flew systematic patterns, their receivers now tuned to the frequencies used by X-Giret. It took less than 48 hours to find the first X-Giret beam complex. It consisted of 4 distinct beams, 1 main beam and 3 cross beams, all converging on a single point in the British Midlands. Jones plotted the beams on a map and felt his stomach drop. The convergence point was Coventry, a city of critical importance to Britain's war production. Coventry hosted numerous aircraft factories, machine tool manufacturers, and munitions plants. It was precisely the kind of high-value target that would justify using the expensive and complex X-Giret system. They're going to hit Coventry, Jones told his superiors, and unless we can develop X-Giret countermeasures immediately, they're going to destroy it. The problem was that X-Giret was far harder to counter than Nicobine. The system used multiple frequencies, making it difficult to jam all of them simultaneously. The automated timing system meant that simple beam bending wouldn't work. Even if the aircraft was slightly off course, the automatic calculator would compensate. Jones needed a different approach. Working almost without sleep, he devised a multi-layered countermeasure strategy. First, British meacons would attempt to interfere with the main X-Giret navigation beam, potentially causing aircraft to approach from slightly incorrect headings. This wouldn't prevent bombing entirely, but it would introduce some targeting error. Second, and more critically, Jones proposed interfering with the crossbeams that the system used for timing calculations. If British transmitters could broadcast false crossbeam signals slightly before or after the real German beams, the automated timing system would receive incorrect data and calculate the wrong bomb release point. We're essentially lying to their computers, Jones explained. We'll make their automated systems think the aircraft is traveling faster or slower than it actually is, which will cause it to drop bombs too early or too late. The technical challenge was enormous. The timing had to be precise. Interfere too much, and the Germans would immediately recognize deliberate jamming. Interfere too little, and the bombs would still hit, close enough to cause catastrophic damage. British engineers worked around the clock to construct the specialized transmitters needed for X-Giret countermeasures. They had days, perhaps hours, to complete systems that normally would have required months of development. The intelligence regarding Coventry became increasingly specific and increasingly urgent. Decoded German messages indicated a major operation was planned for the night of November 14, 1940. The codename was Unternehmen. Mondschein Sonata, Operation Moonlight Sonata. Jones found himself in the center of a moral and strategic nightmare. The intelligence was good enough that he was confident Coventry would be the target. The X-Giret countermeasures were in place, but were largely untested. British air defenses could be reinforced, but doing so too obviously might alert the Germans that their plans had been compromised. On the morning of November 14th, Jones attended a meeting at 10 Downing Street. Prime Minister Winston Churchill was present, along with senior military commanders and intelligence officials. Churchill, characteristically direct, asked the question everyone was thinking, "Dr. Jones, what are our options?" Jones took a deep breath. "Prime Minister, we have several options, none of them perfect. We can attempt full evacuation of Coventry's civilian population, which would save lives, but would certainly alert the Germans that we have prior knowledge of their plans. We can deploy every fighter and anti-aircraft gun we have to Coventry's defense, which might reduce the damage, but would similarly indicate foreknowledge. Or we can prepare as if for a routine raid, use our beam countermeasures, and hope they're effective enough to prevent catastrophic damage. And if the countermeasures fail? Churchill asked quietly, "Then Coventry will burn, sir, and many people will die." The room fell silent. The weight of decision hung heavy in the air. These were the impossible choices that war demanded. Choices where every option involved death. And the question was only how much, and at what cost. The decision that emerged was a painful compromise. Coventry's authorities would be warned to expect a major raid, and should prepare accordingly, but without specific details that would indicate precise foreknowledge. Air defenses would be reinforced, but not to an extent that would seem unusual. The ex-Juret countermeasures would be activated, but nothing would be done that would definitely reveal to the Germans that their beam systems had been compromised. Jones left the meeting feeling physically ill. He understood the logic. Protecting the intelligence source was critical for the long-term prosecution of the war. If the Germans knew their communications were being read and their beam systems compromised, they would change everything, and Britain would lose invaluable intelligence advantages. But understanding the logic didn't make it hurt any less. That evening, Jones was in the countermeasures control center as German bombers began assembling over France. Radio operators monitored multiple frequencies, tracking the ex-Juret beams as they activated. "Main beam is active," an operator reported. "Bearing 075 degrees, converging on Coventry as predicted. Cross beams activating now." "Begin countermeasures," Jones ordered. British transmitters came alive, broadcasting their false beams carefully timed to interfere with the German ex-Juret signals. Operators watched their displays intently, making minute adjustments to maximize interference without making it too obvious. Over Coventry, air raid sirens began their mournful wail. Citizens who had heard such warnings dozens of times before took shelter once again, hoping this would be just another raid with a few scattered bombs and perhaps a building or two damaged. They had no idea what was about to hit them. The first German bombers arrived around 1930 hours. They were pathfinders from Kampfgruppe 100, using ex-Juret to identify and mark the target for the main bomber stream that would follow. Aboard the German aircraft, pilots concentrated on their instruments. They flew along the main beam, listening to the characteristic tone that indicated proper alignment. Their specialized ex-Juret equipment was functioning normally, showing them crossing the first crossbeam, then the second, with the automatic timing system activating as designed. But what the German equipment was detecting wasn't just the real beams from German transmitters. It was those beams corrupted and confused by British countermeasures. The timing data being fed to the automatic bomb release computers was subtly wrong. When the first ex-Juret-equipped bombers released their marker flares, many fell outside the intended target zones. Some landed in residential areas on the city's outskirts. Others fell in open fields. The precise targeting the system was supposed to provide had been degraded into something more like conventional bombing. Still dangerous, but far less accurate. The main bomber stream followed, guided by the scattered marker flares. Without ex-Juret of their own, these bombers relied on Knickebein beams, and the visual markers dropped by the pathfinders. But the markers were dispersed over a wide area, and Knickebein was being jammed by British meakins, so the bombing became scattered and unfocused. It was still terrible. Hundreds of bombers dropped thousands of tons of explosives and incendiaries on Coventry over the course of 11 hours. The medieval cathedral was destroyed. Hundreds of buildings burned. Hundreds of civilians died. And thousands were made homeless. But it could have been far worse. Analysis after the raid showed that the majority of bombs had fallen outside the primary industrial areas, that had been the Germans' intended targets. The aircraft factories were damaged, but not destroyed. Production was disrupted, but not halted. The city's infrastructure remained largely functional. The ex-Jurat countermeasures had worked. Not perfectly, but well enough to prevent the surgical destruction the Germans had planned. In the days following the Coventry raid, German bomber crews reported increasing unreliability with their ex-Jurat equipment. Sometimes it worked perfectly. Other times it seemed to give incorrect information. German engineers began a frantic troubleshooting process, never suspecting that the equipment problems they were diagnosing were actually deliberate British interference. Kampfgruppe 100 continued flying missions using ex-Jurat, but with declining confidence in the system's accuracy. Increasingly, they reverted to conventional bombing methods, negating the precision capability that had made them so dangerous. By early 1941, German faith in ex-Jurat had eroded significantly. The system remained in use, but it was no longer the war-winning precision weapon that German planners had envisioned. Jones had won another round in the invisible war, as British countermeasures progressively neutered Nicobine and ex-Jurat. German scientists worked frantically on next-generation systems. In intelligence intercepts from early 1941, Jones began noticing references to a new development. Wotan. In Norse mythology, Wotan, or Odin, was the one-eyed god, chief of the pantheon. The mythological reference gave Jones an immediate clue about the system's nature. One eye, he mused to Charles Frank. Wotan has one eye. What if this new system uses just one beam instead of the multiple beams used by Nicobine and ex-Jurat? Frank frowned. But how would that work? You need at least two beams to establish a precise position, one for navigation and one to mark the target. Unless, Jones said slowly, his mind racing through possibilities, unless the system measures distance along the beam as well as direction. If they can measure how far along a single beam the aircraft is located, they don't need a second beam for positioning. It was a brilliant insight, and it proved to be correct. As more intelligence accumulated, Jones pieced together how the Wotan system, technically designated WWII, actually operated. WWII used a single, highly precise beam for navigation, just like Nicobine. But it added something revolutionary, a transponder system. Ground equipment would send an interrogation signal to the aircraft. The aircraft's transponder would automatically respond. By measuring the precise time delay between sending the interrogation and receiving the response, ground controllers could calculate the aircraft's distance from the transmitter. With one measurement giving direction, the beam itself, and another giving distance, the transponder range, German controllers could precisely locate their aircraft and guide them to targets. Even more sophisticated, the German ground controllers could continuously track the aircraft's position and directly tell pilots when to release their bombs. It was almost like remote control bombing. This is more advanced than anything they've deployed before, Jones told senior RAF officers. It's not just guidance, it's command and control. German ground controllers will be able to manage bombing runs with extraordinary precision. The technical challenge of countering WWII was unlike anything Jones had faced. Simply jamming the beam wouldn't work. The Germans would immediately recognize deliberate interference. Jamming the transponder system would similarly be too obvious. Jones needed something more subtle, and in a flash of insight, he realized what it had to be. Deception through mimicry. What if, he proposed to his engineering team, we build our own transponder system? When German ground control sends an interrogation signal, our equipment responds, as well as the real aircraft transponder. The German controllers receive multiple responses, one from their actual aircraft and additional responses from our system. Cockburn immediately saw the potential. They wouldn't know which response was genuine. They'd get conflicting information about their aircraft's position. They'd think their equipment was malfunctioning. Exactly, Jones confirmed. And if we're clever about it, we can make our false responses indicate positions slightly different from the aircraft's actual location. The German controllers would be trying to guide bombers based on faulty position information. They'd give bomb release commands at the wrong time, missing their targets. It was electronic warfare of a sophistication that had never been attempted. The British would essentially be inserting themselves into the German control loop, feeding false information to confuse the entire targeting system. The technical implementation was extraordinarily challenging. British engineers had to first capture and analyze an actual WWII transponder to understand its exact operating characteristics. Then they had to build ground-based equipment that could detect German interrogation signals, determine the appropriate false response, and transmit that response with precise timing to create the desired confusion. An opportunity came in March 1941, when a German bomber equipped with WWII made an emergency, landing on the British coast after being damaged by anti-aircraft fire. The crew was captured, and critically, the aircraft's transponder equipment was recovered intact. Jones and his team descended on the aircraft like archaeologists examining an ancient treasure. They photographed every component, traced every circuit, and tested every function. Within a week, they understood WWII's operation in minute detail. Armed with this knowledge, British engineers began constructing what they called false responder stations. These would be positioned near likely German bombing targets and programmed to interfere. With WWII operations, the first operational test came on a night when intelligence indicated a WWII-equipped bomber would be targeting a naval facility in Portsmouth. British false responder equipment activated as the German aircraft approached. German ground controllers sent their standard interrogation signals, expecting to receive a single clear response from their aircraft's transponder. Instead, they received multiple responses indicating slightly different positions. Position uncertain, the ground controller radioed to the bomber crew. Equipment shows conflicting range data. Proceed with caution. The bomber crew, following their training, continued along the guidance beam. But the conflicting position information made precise bombing impossible. The ground controller couldn't accurately determine when to issue the bomb release command. Eventually, the frustrated German pilot released his bombs based on his best estimate of position. They fell in the ocean, half a mile from shore. Similar results occurred on subsequent missions. WWII, which was supposed to be the Luftwaffe's ultimate precision bombing system, proved to be unreliable and frustrating. German crews increasingly distrusted the system, and planners began questioning whether its complexity was worth the minimal improvement over conventional bombing methods. By mid-1941, all three German beam bombing systems, Nickebein, X-Juret, and Y-Juret, had been effectively neutralized by British countermeasures. The Luftwaffe's technological advantage in precision, night bombing had been completely eliminated. The invisible war had been won by the defenders. While operational countermeasures were achieving tactical success, Jones remained focused on a deeper question. How could British defenses be made even more effective? The answer, he realized, lay in understanding antenna technology more thoroughly than the Germans themselves. An antenna is essentially a transducer that converts electrical signals into electromagnetic waves for transmission or electromagnetic waves into electrical signals for reception. The design of an antenna determines how it radiates or receives energy in different directions. The German beam systems relied on highly directional antennas that focused radio energy into narrow beams. British countermeasures were working, but they required significant power and weren't always perfectly effective. Because British antennas couldn't match the directional precision of German designs, Jones began an intensive study of antenna theory, working through complex mathematics that described electromagnetic radiation patterns. He consulted with Britain's leading radio engineers and spent countless hours reviewing German technical documents recovered from captured equipment. What he discovered was that the Germans were using a type of antenna array called a WWII array, named after the Japanese engineers, who had invented it in the 1920s. This design used multiple antenna elements arranged in a specific geometric pattern to create highly directional radiation, but Jones found something the Germans had apparently missed. By modifying the spacing and length of the antenna elements, he could create patterns that weren't just directional, but that could be specifically tuned to cancel out other beams. He called these interference antennas. They were designed not to broadcast their own beams, but to create electromagnetic interference patterns that would precisely overlap and neutralize German beams. The physics was complex, involving careful calculation of wavelengths, element spacing, and phase relationships. But the result was revolutionary. British transmitters equipped with Jones's interference antennas could counter German beams with a fraction of the power previously required and with far greater precision. Professor Robert Watson Watt, the pioneering radar developer, reviewed Jones's antenna designs and was impressed. "Reggie, these designs show real innovation. You're not just jamming German signals. You're creating anti-signals that destructively interfere with them at a fundamental level. It's elegant physics applied to a practical military problem." Production of the new antenna systems began immediately. Within months, the network of British countermeasure stations was upgraded with Jones's improved designs. The result was a dramatic increase in effectiveness. German bomber crews now reported that their beam navigation systems were almost completely unreliable over British airspace. What had been an intermittent problem became a constant one. The Luftwaffe's technical services investigated frantically, never fully understanding that they were facing carefully engineered countermeasures rather than atmospheric anomalies or equipment defects. The antenna work had another consequence. It established Jones as one of Britain's leading experts on radio frequency systems, a reputation that would serve him well when he uncovered something even more significant than beam bombing systems. By late 1942, the beam bombing threat had largely subsided. The Luftwaffe still conducted raids on British cities, but without the precision guidance systems that had made them so dangerous in 1940-41. Jones's countermeasures had effectively ended Germany's technological advantage in this area, but Jones's work hadn't ended. His role had evolved from focusing solely on beam systems to serving as the Air Ministry's primary scientific intelligence analyst for all German technical developments. And in this capacity, he began noticing disturbing references in intelligence reports to research facilities on the Baltic coast. The location was called Peenemünde, situated on a remote peninsula in northern Germany. Intercepted communications mentioned special weapons, long-range projectiles, and experimental tests. Reconnaissance photographs showed unusual facilities, large buildings, strange circular structures, and what appeared to be extensive testing ranges. Jones began collecting every fragment of intelligence related to Peenemünde. A captured German document here, an intercepted radio message there, reports from resistance networks in occupied territories. Slowly, piece by piece, he assembled information about what was happening at this mysterious facility. What emerged was deeply concerning. The Germans were apparently developing rocket weapons, not small battlefield rockets, but large missiles capable of carrying substantial warheads across distances of hundreds of miles. At a meeting with military leaders, Jones presented his findings. The reaction was mixed. Some were dismissive. Rockets capable of such range and payload seemed like science fiction. Others were intrigued but skeptical about the immediacy of the threat. "Dr. Jones," asked Air Chief Marshal Portal, "rockets are all well and good in theory, but do you have concrete evidence that the Germans have actually built operational weapons?" Jones had to admit he didn't. "Not operational weapons, sir, but certainly an advanced development program. The evidence suggests they've conducted successful long-range tests. I believe they're moving toward deployment. Belief isn't enough, Portal replied. We need hard evidence before we can justify diverting bombing resources to attack these facilities. Jones understood the challenge. Britain's bomber forces were already stretched thin, conducting strategic bombing campaigns against German industry and military targets. Attacking Peenemünde would require a major operation that would draw resources from other objectives. But if the Germans were really developing long-range rocket weapons, the threat was existential. Unlike aircraft, rockets couldn't be intercepted by fighters or brought down by anti-aircraft fire. If launched in sufficient numbers, they could devastate British cities with no effective defense possible. The breakthrough came from an unexpected source. In May 1943, a member of the Danish resistance photographed unusual activity at a German testing site. The photographs showed what appeared to be a large rocket-like object on a launch platform. When these photographs reached Jones's desk, he studied them with growing excitement and dread. The object was clearly not an aircraft. It had a cylindrical body, pointed nose, and what appeared to be stabilizing fins at the base. It was exactly what a large rocket would look like. He immediately requested high-altitude reconnaissance flights over Peenemünde, RAF photographic reconnaissance Spitfires, flying at extreme altitude to avoid detection, captured images of the facility in unprecedented detail. Photo interpreters working with Jones identified multiple launch platforms, storage buildings, and, most telling, several rocket-like objects in various stages of assembly. The evidence was now undeniable. Gentlemen, Jones told a meeting of the Defense Committee, the Germans have developed operational rocket weapons. Based on the size of the rockets observed at Peenemünde, I estimate they can carry a 1-ton warhead over a range of at least 200 miles. London is well within that range. If deployed in numbers, these weapons could deliver explosive tonnage comparable to conventional bombing raids, but with no possibility of interception. Winston Churchill, attending the meeting personally, grasped the implications immediately. How do we stop this? We have to attack Peenemünde directly, Jones replied. Destroy the production facilities, kill the scientists and engineers working on the program, and set back their development timeline. It's the only way to prevent or delay deployment. The decision was made. The RAF would conduct a massive bombing raid on Peenemünde, attacking the facility with everything they could bring to bear. The raid on Peenemünde, codenamed Operation Hydra, was planned for the night of August 17-18, 1943. It would be one of the largest precision bombing raids of the war, involving nearly 600 heavy bombers carrying a mix of high-explosive and incendiary bombs. Jones was intimately involved in planning the raid. His intelligence had identified the most critical buildings, the assembly halls where rockets were manufactured, the technical facilities where they were tested, and the residential areas where key scientists and engineers lived. The targets were chosen with cold calculation. Destroying facilities was important, but killing the expertise needed to rebuild those facilities was equally critical. It was the harsh arithmetic of total war. The raid itself was extraordinarily costly. The Luftwaffe, recognizing the importance of Peenemünde, defended it vigorously. British bombers faced heavy anti-aircraft fire and night fighter attacks. 40 aircraft were lost, with their crews killed or captured. But the raid achieved its objectives. Aerial photographs taken in the following days showed extensive destruction. Assembly buildings were collapsed ruins. Testing facilities were damaged beyond immediate repair. And tragically for the German program, many key personnel had been killed, including Dr. Walter Thiel, the chief rocket engine designer. The German rocket program was set back by months, perhaps years. V-2 rockets would eventually be used against London starting in September 1944, but in smaller numbers and with less effectiveness than originally planned. The raid Jones had helped plan had saved thousands of lives by disrupting the program when it was most vulnerable. But Jones would discover only after the war that Peenemünde had been hiding, an even more significant secret. In the immediate aftermath of Germany's surrender in May 1945, Allied intelligence teams fanned out across German territory, securing documents and interrogating scientists. Jones, as one of Britain's senior scientific intelligence officers, participated in this effort. What he discovered shocked him. Peenemünde hadn't just been developing rockets. It had served as a coordination center for multiple advanced weapons programs, including research into atomic energy. German scientists had been working on nuclear fission, attempting to develop atomic weapons or at least atomic power sources. The program hadn't succeeded. German nuclear research never reached the stage of building an operational atomic bomb, but it had been much more advanced than Allied intelligence had realized during the war. And here's what made Jones's blood run cold. The August 1943 bombing raid on Peenemünde hadn't just disrupted rocket development. It had also scattered the nuclear research program, killing key personnel and destroying facilities that supported atomic research. "We were aiming at rockets," Jones told an American intelligence officer months after the war, "and we hit something much bigger without even knowing it." If Operation Hydra had never been carried out, if Peenemünde had continued operating without disruption, would German nuclear research have progressed to the point of creating usable weapons? Nobody could say for certain, but the possibility haunted Jones. His investigation of beam-bombing systems in 1940 had led to discoveries about rockets in 1943, which had inadvertently disrupted nuclear weapons research. The chain of consequences was staggering. A single young physicist's refusal to dismiss an impossible technology had potentially saved the world from nuclear warfare years before. Atomic bombs were actually used. When the war ended, Reginald Victor Jones was just 34 years old. He had spent 6 years in a state of perpetual intellectual combat, constantly adapting to new threats and developing innovative countermeasures. The pace had been exhausting, but Jones had thrived under the pressure. Now, with victory achieved and the immediate threats eliminated, he faced a question. What next? The British government wanted him to continue in scientific intelligence. The Cold War was already beginning, and the Soviet Union presented many of the same challenges that Germany had: a technologically sophisticated adversary developing advanced weapons systems that needed to be understood and countered. But Jones was tired. He had spent his 20s and early 30s fighting an invisible war under enormous pressure. He wanted to return to pure scientific research, to pursue knowledge for its own sake, rather than as a weapon against enemies. In 1946, he accepted a professorship at the University of Aberdeen in Scotland, where he would teach physics and conduct research for the next 35 years. He trained hundreds of students, many of whom went on to distinguished careers in science and engineering. But Jones never completely left the world of intelligence. He served as a consultant to British defense agencies, provided expert testimony on scientific matters related to national security, and maintained connections with the intelligence community throughout his life. His wartime work remained largely classified for decades. When portions of the beam warfare story were declassified in the 1970s, Jones wrote his memoirs, Most Secret War, detailing the invisible battles he had fought. The book became a bestseller and established Jones as one of the unsung heroes of World War II. He received numerous honors, including a knighthood in 1994, making him Sir Reginald Jones in recognition of his wartime service. In his later years, Jones frequently gave lectures and wrote essays about the lessons he had learned from scientific intelligence work. His insights were profound and remain relevant today. Intelligence isn't about knowing everything, he would tell students. It's about knowing the right things. During the war, I was flooded with information. Intercepted messages, reconnaissance photographs, captured documents, reports from agents. The challenge wasn't gathering information, but interpreting it correctly. He emphasized the importance of maintaining an open mind while remaining skeptical. When everyone tells you something is impossible, that should make you curious, not dismissive. The beam systems were impossible according to conventional wisdom. Rockets capable of reaching London from Germany were impossible. Yet the Germans were developing both. A good intelligence analyst has to be willing to believe in the possible impossibility. Jones also reflected on the ethical dimensions of intelligence work. The Coventry bombing, in particular, had troubled him for decades. We knew the attack was coming. We could have saved more lives, but doing so would have revealed our knowledge, compromising future intelligence. Was that the right choice? I still don't know. He argued that scientists working in national security roles have special ethical responsibilities. We create knowledge that can kill. That's an awesome responsibility. Every calculation I made, every countermeasure I designed, had human consequences. Scientists can't hide behind, "I was just doing my job," or "I was just following orders." We have to own the consequences of our work. But he also staunchly defended the necessity of scientific intelligence. Some people have romantic notions of warfare, brave soldiers fighting honorably on battlefields. Modern war isn't like that. It's fought as much in laboratories and factories as on battlefields. The side with better technology, better intelligence, and better scientific understanding has an enormous advantage. Britain survived partly because we were better at scientific intelligence than Germany. We understood their capabilities before they could fully exploit them. The techniques Jones pioneered during the beam warfare battles became foundational to modern electronic warfare. Every military today employs electronic warfare specialists who use methods directly descended from Jones's wartime innovations. The basic principles he established remain current. Detection and analysis. Before you can counter an enemy's electronic systems, you must detect and thoroughly understand them. Jones's methodical approach to analyzing German beam systems, intercepting signals, recovering equipment, conducting technical analysis, and building comprehensive models of how systems operated, became the standard methodology for technical intelligence. Subtle countermeasures. Jones's insight that effective countermeasures should confuse, rather than obviously block enemy systems, revolutionized electronic warfare. Modern military forces use sophisticated jamming and spoofing techniques designed to make enemy systems unreliable without immediately revealing that they're under attack. Adaptive response. Jones constantly adapted his countermeasures as German technology evolved. This established the principle that electronic warfare is an ongoing competition requiring continuous innovation. Military forces now maintain permanent electronic warfare research programs specifically to stay ahead of adversaries. Integration of intelligence and operations. Jones broke down barriers between intelligence analysts and operational forces. He didn't just identify threats. He developed practical countermeasures and worked directly with operators to deploy them. This integrated approach is now standard in military operations. Beyond military applications, Jones's work contributed to civilian technology development. The antenna designs he pioneered influenced everything from radio astronomy to satellite communications. His work on signal processing helped lay groundwork for technologies we now use daily: Wi-Fi, GPS, cellular networks. Despite his achievements, Jones paid a personal price for his wartime service. The years of intense stress, irregular hours, and enormous responsibility took a toll on his health. He suffered from stress-related ailments for years after the war. His relationships were strained. He married Dorothy Ethel Mary Stewart in 1940, at the height of the beam warfare crisis. Their early years together were dominated by the demands of his classified work, which he couldn't discuss with her. Many nights he slept at the office or didn't sleep at all. Winning the war Nearly cost me my marriage, he admitted decades later. Dorothy put up with an absent husband who couldn't explain where he was or what he was doing. I'm not sure I'd have been as patient in her position. He also struggled with what we would now recognize as symptoms of post-traumatic stress. The constant pressure of knowing that lives depended on his analyses, the impossible choices like Coventry, the awareness that mistakes would have catastrophic consequences. All of this left psychological scars. In his memoirs, Jones wrote with remarkable candor about the emotional toll. People think of scientific work as dry and unemotional, mathematics and measurements and careful logic. But when your calculations determine whether people live or die, it becomes intensely emotional. Every time we detected a new German beam pointing at a British city, I knew that if I couldn't develop countermeasures quickly enough, people would die. That knowledge sat on my chest like a physical weight. He found healing through his post-war academic career, teaching students who hadn't lived through the war, and conducting research purely for the advancement of knowledge rather than military advantage. But he never completely left the war behind. It had shaped him too fundamentally. For decades, Jones's contributions were little known outside classified circles. The nature of his work meant it couldn't be publicly acknowledged, and he was forbidden from discussing specifics. While military heroes received medals and public acclaim, Jones remained anonymous. This began to change in the 1970s, when portions of Britain's wartime scientific intelligence work were declassified. Jones was finally able to publish his memoirs and speak publicly about his experiences. Recognition came late, but was substantial. He received the Medal of Freedom from the United States in 1946. Shortly after the war, one of the few honors he could accept at the time, since it could be presented for unspecified wartime service. Later honors included Commander of the Order of the British Empire, CBE, in 1942, Companion of the Order of the Bath, CB, in 1946, Fellow of the Royal Society in 1965, Knighthood, KBE. In 1994, he received honorary doctorates from multiple universities and numerous academic prizes. Recognizing his contributions to physics and intelligence methodology, perhaps more meaningful to Jones than official honors was the recognition from former colleagues and adversaries. German scientists who had worked on the beam systems and rocket programs, upon learning after the war who had been countering them, expressed grudging admiration. "We thought we were facing an entire organization," one German engineer told Jones at a post-war technical conference. "We never imagined it was essentially one man with a small team. If we had known, we might have despaired." How does one compete against such focused brilliance? In his final years, Jones frequently reflected on what his experiences could teach future generations. Several themes emerged repeatedly in his lectures and writings. The value of interdisciplinary thinking. Jones succeeded because he could think across disciplinary boundaries. He combined physics, engineering, intelligence analysis, operational planning, and creative problem-solving. "The most interesting problems," he said, "sit at the intersections between disciplines. Don't let yourself be trapped in a single specialty." Question everything. Jones's greatest discoveries came from questioning assumptions everyone else accepted. When someone tells you, "That's impossible," what they often mean is, "I don't understand how to do that." Don't confuse your own ignorance with fundamental impossibility. Details matter. Jones was meticulous in his analysis, understanding that small details could reveal large truths. A single technical specification recovered from a crashed aircraft, a single phrase in an intercepted message. These tiny fragments could unlock entire systems if you knew how to interpret them. Think like your adversary. Jones succeeded by imagining himself as a German engineer. What would he try to build? What limitations would he face? What clever solutions might he devise? You can't counter what you don't understand, he emphasized. And you can't understand your adversary's capabilities without thinking deeply about their challenges and constraints. Ethics must guide technology. Jones was adamant that scientists have ethical responsibilities that transcend orders or institutional loyalty. Science gives us power. Ethics must guide how we use that power. I'm proud of saving British lives through my work. I'm troubled by how many people, German civilians, German scientists, died as a result of operations I helped plan. Both things are true. Science isn't ethically neutral, and scientists must own the consequences of their work. Persistence over brilliance. When asked about the secret to his success, Jones consistently deflected praise for his intelligence and instead emphasized persistence. I wasn't the smartest physicist in Britain, but I was willing to keep working a problem when others gave up. I'd stare at data for hours, looking for patterns. I'd pursue leads that seemed unlikely. Success in intelligence work comes more from persistence than from genius. Reginald Victor Jones retired from Aberdeen University in 1981 at the age of 70. But retirement didn't mean inactivity. He continued writing, lecturing, and consulting for another decade and a half. He became a popular public speaker, known for presenting complex scientific concepts in accessible ways and telling engaging stories from his wartime experiences. His lectures mixed technical explanation with human drama, making scientific intelligence fascinating to general audiences. He maintained close friendships with other figures from the wartime scientific community: Robert Watson Watt, Robert Cockburn, Charles Frank. They would gather regularly, sharing memories and reflecting on how their work had shaped the post-war world. Jones watched with interest as electronic warfare techniques evolved far beyond what had been possible in the 1940s. Modern militaries employ extraordinarily sophisticated systems for detecting, analyzing, and countering enemy electronics, systems built on principles Jones had pioneered. He saw the Cold War come and go, witnessed the collapse of the Soviet Union, and observed the emergence of new technological challenges in warfare and intelligence. In his final years, he expressed concern about cyber warfare and information operations, recognizing them as evolutionary descendants of the invisible war he had fought decades earlier. "The battlefield keeps changing," he observed in a 1995 lecture, "but the fundamental principles remain. Understand your adversary's capabilities. Develop innovative countermeasures. Stay ahead of the threat." These principles applied in 1940. They applied throughout the Cold War, and they'll apply in whatever conflicts come next. Reginald Victor Jones died on December 17, 1997, at the age of 86. His obituaries appeared in major newspapers worldwide, finally giving public recognition to a man whose secret war had helped save Britain. The Battle of the Beams, as it came to be known, fundamentally transformed how nations approach intelligence gathering and analysis. Before Jones's work, intelligence was primarily focused on human sources: spies, defectors, informants, and traditional code-breaking. Technical intelligence existed, but was considered a specialized niche. Jones proved that scientific analysis could be as valuable as any spy network. He showed that technical systems could be reverse-engineered from fragmentary evidence, that enemy capabilities could be predicted from theoretical principles, and that effective countermeasures could be developed even without complete information. After the war, every major military establishment created scientific and technical intelligence branches modeled directly on the organization Jones had built. The United States established the Scientific Intelligence Branch within the CIA, later evolving into the Directorate of Science and Technology. The Soviet Union created similar organs within the KGB and GRU. The methods Jones pioneered became standard practice. Technical collection. Systematic monitoring of electromagnetic emissions to identify adversary systems and capabilities. Modern signals intelligence SIGINT, traces directly to Jones's beam detection efforts. Material exploitation. Detailed analysis of captured equipment to reverse engineer its operation and identify vulnerabilities. The crashed German bombers Jones examined were early examples of what's now routine practice. Scientific modeling. Using theoretical understanding to predict enemy capabilities before they're deployed. Jones's anticipation of WWII, based on incremental improvements over previous systems, established this approach. Integrated countermeasures. Developing defensive or offensive responses tailored to specific technical characteristics of enemy systems. Modern electronic warfare is essentially a direct descendant of Jones's beam countermeasures. One of Jones's less celebrated but highly consequential contributions was his advancement of antenna technology. His work designing interference antennas to counter German beams required pushing the boundaries of electromagnetic theory and engineering. The mathematics of antenna arrays, understanding how multiple antenna elements interact to create complex radiation patterns, was not well developed in the 1940s. Jones had to work through much of this theory himself, combining electromagnetic field theory with practical engineering constraints. His designs influenced civilian antenna technology for decades after the war. Television antennas, radio telescopes, and eventually cellular phone towers all benefited from advances in directional antenna design that Jones and his colleagues pioneered. In a curious historical footnote, some of the antenna theory Jones developed for military countermeasures was later published in academic journals, after appropriate delays for declassification, and became standard. References in electrical engineering education. Thousands of engineers learned antenna design from textbooks that incorporated principles first worked out in the desperate urgency of wartime. Perhaps Jones's most profound legacy was demonstrating how innovation could flourish, even under extreme pressure. The countermeasures he developed weren't the result of large, well-funded research programs with ample time for development. They were created by small teams working against impossible deadlines with limited resources. Yet they succeeded because Jones created a culture that encouraged creative thinking, rewarded unconventional approaches, and valued problem-solving over bureaucratic process. Some principles from Jones's approach to innovation. Flat hierarchies. Jones, despite being relatively junior in age and rank, had direct access to the highest levels of decision-making. When he had a critical insight, he could present it immediately to air chief marshals and cabinet ministers without going through layers of bureaucracy. Interdisciplinary collaboration. Jones's team included physicists, engineers, mathematicians, cryptographers, and operational military personnel. He deliberately mixed specialists from different fields, finding that the creative friction generated new insights. Tolerance for failure. Many of Jones's ideas didn't work. Experimental countermeasures that failed in testing, theoretical predictions that proved incorrect, operational plans that didn't achieve desired results. These failures were treated as learning opportunities rather than career-ending mistakes. Rapid prototyping. Jones insisted on building and testing countermeasures quickly, even if they weren't perfect. A working but imperfect solution deployed immediately was better than a perfect solution that took months to develop. Objective analysis. Jones cultivated a culture where evidence trumped rank. If a junior technician noticed something in data that contradicted Jones's own interpretation, that observation was taken seriously and investigated. These organizational and cultural practices were as important as any specific technical innovation. After the war, they influenced how research and Development organizations were structured across government and industry. Historians have long debated how differently World War II might have unfolded if Jones had not discovered and countered German beam bombing systems. While counterfactual history is inherently speculative, we can make some informed assessments. Without effective countermeasures, German precision bombing would have been devastatingly effective. Britain's aircraft production, centered in Coventry and other Midlands cities, would have been severely disrupted. Port facilities, command and control centers, and logistical infrastructure could have been systematically destroyed. Britain's ability to continue fighting would have been compromised. Without adequate aircraft production, the RAF's strength would have declined, making defense against both bombing and a potential invasion increasingly difficult. Without functioning ports, imports of food and materiel from North America would have been disrupted, threatening Britain's ability to sustain its population and military. It's entirely plausible that without Jones's countermeasures, Britain might have been forced to negotiate some form of settlement with Germany, potentially as early as 1941. At minimum, the war would have lasted longer and cost many more lives. The Peenemünde raid's disruption of German rocket and nuclear programs is harder to quantify, but potentially even more significant. If V-2 rockets had been deployed in larger numbers and earlier in the war, they would have caused substantially more damage to London and other British cities. There was no effective defense against ballistic missiles in the 1940s. Even more consequential, if German nuclear research had progressed to weapons development, the entire course of the war and subsequent history would have been altered beyond recognition. The atomic attacks on Hiroshima and Nagasaki in 1945 demonstrated what nuclear weapons could do. If Germany had acquired such weapons years earlier, the consequences would have been catastrophic. Jones himself was reluctant to engage in such speculation. "I did what was necessary at the time," he would say. Trying to imagine how history might have been different if I'd failed is an exercise in narcissism. Many people contributed to victory. I was just one. But historians and military analysts have been less modest on his behalf, with many arguing that Jones's contributions were as significant as those of any general or admiral, and possibly more consequential than most. One aspect of Jones's story that often gets overlooked is its human dimension. Discussions of the Battle of the Beams tend to focus on technical details, frequencies, antenna designs, countermeasures. But behind all of that was a group of human beings working under extraordinary stress. Jones's team consisted mostly of young people, physicists and engineers in their 20s and 30s. Many pulled from academic careers just beginning. They worked brutal hours, often sleeping on cots in their offices. They dealt with constant pressure, knowing that mistakes could cost thousands of lives. Relationships formed under such conditions were intensely close. Charles Frank, Jones's closest collaborator, remained a lifelong friend. They would exchange letters and visit regularly, right up until Frank's death in 1998. Just months after Jones's own passing, Robert Cockburn, who had worked on the engineering implementation of countermeasures, later said, "Those years were simultaneously the worst and best of my life. The pressure was unbelievable, but the sense of purpose, of doing something genuinely important, I've never experienced anything like it since." Not everyone handled the pressure well. The team experienced mental health crises, relationship breakdowns, and burnout. Some members required reassignment to less stressful duties. Jones himself came close to collapse several times, saved largely by his ability to compartmentalize stress and maintain focus on problems rather than on emotions. The human cost extended beyond Jones's immediate team. The German scientists and engineers who developed the beam systems were, in many cases, simply doing their jobs with no particular ideological commitment to Nazi aims. Many were killed in the Peenemünde raid and other Allied attacks on German technical facilities. Jones struggled with this throughout his life. "They were colleagues, in a way," he reflected in a 1990 interview. "We were solving similar problems, just from opposite sides. Some of them I met after the war. Good people, decent people. But during the war, my job was to defeat them, and that often meant killing them. I've made peace with that necessity, but I won't pretend it doesn't trouble me. Jones took his role as an educator seriously, seeing teaching as a way to pass on not just scientific knowledge, but also the problem-solving approaches he had developed during the war. His students at Aberdeen University received rigorous technical training, but Jones also emphasized creativity, persistence, and ethical responsibility. Many of his students went on to distinguished careers in science, engineering, and defense work. Some became professors themselves, passing on what they had learned from Jones to yet another generation. When former students gathered for Jones's 80th birthday celebration in 1991, they shared stories about his teaching methods. Jones didn't lecture in the traditional sense, reading from notes or working through standard material. Instead, he would present problems and work through solutions in real time, showing students not just answers, but the thinking process that led to answers. "He taught us to think," said one former student who had become a professor of electrical engineering. Not to memorize, not to apply formulas mechanically, but to actually think through problems from first principles. That was his gift as a teacher. Jones was particularly effective at demonstrating how theoretical knowledge connected to practical applications. He would frequently use examples from his wartime work to show students how abstract mathematics or physics could solve real-world problems. "You're not just learning Maxwell's equations," he would tell students studying electromagnetic theory. "You're learning tools that can detect enemy weapons, design communication systems, or develop medical imaging technology. The equations are just symbols on paper until you apply them to actual problems." One of the more challenging aspects of Jones's wartime experience was the burden of secrecy. His work was classified at the highest levels, and he was forbidden from discussing it with anyone not specifically cleared for access. This meant that even close friends and family members couldn't know what he did or why it mattered. His parents knew he worked for the government in some scientific capacity, but had no idea of the significance of his contributions. His wife knew even less for most of the war years. After the war, the classification continued for decades. Jones couldn't publish papers about his work, couldn't receive public recognition, and couldn't share his experiences even in social settings. When asked what he had done during the war, he had to deflect with vague answers about government scientific work. This took a psychological toll. Recognition and acknowledgement are important to most people, and Jones was no exception. He took pride in what he had accomplished and found it frustrating to be unable to share that with others. The secrecy also complicated historical understanding. For decades after the war, military histories of the Blitz and Britain's air defense focused on fighter pilots, anti-aircraft gunners, and civilian resilience, all important, but incomplete without understanding the invisible technical battle that had been occurring simultaneously. When declassification finally began in the 1970s, Jones could at last tell his story. The publication of his memoirs, Most Secret War, was personally important to him beyond its commercial success or critical acclaim. It represented finally being able to share the full truth of what had happened. "For 30 years, I carried secrets I couldn't share," he wrote in the book's introduction. "Now, finally, I can tell the story. Not for my own glorification, but so that history can be complete. What happened during those years mattered. People should know about it." In his later years, Jones became increasingly engaged with questions about the ethical responsibilities of scientists and engineers, particularly those working on military applications. His own experience had given him deep insight into these issues. He had created countermeasures that saved British lives, but had also helped plan attacks that killed German scientists and civilians. He had worked on technologies designed explicitly to kill or confuse enemy forces. He had made decisions that affected whether people lived or died. Jones argued forcefully against the notion that scientists could be ethically neutral. simply following orders or pursuing knowledge without regard for consequences. "We create capabilities," he said in a 1985 lecture on science and ethics. "Those capabilities will be used, and we bear some responsibility for how they're used." But he also rejected the opposite extreme, the idea that scientists should refuse to work on military applications or that such work was inherently immoral. Britain was fighting for survival against a genuinely evil regime. Working to defend against that was not just ethically permissible, it was ethically required. Pacifism is a luxury that becomes irresponsible when confronting existential threats. His position was more nuanced. Scientists must engage with the ethical dimensions of their work, must consider consequences, and must be willing to refuse work they genuinely believe to be immoral. But in wartime, especially when facing an adversary like Nazi Germany, defensive and deterrent technologies were ethically necessary. The beam countermeasures saved lives, Jones argued. Not just British lives, German lives too. Every raid that missed its target because of our countermeasures meant German bombers not encountering fighter or anti-aircraft defenses, meant German crews not being shot down. The killing was minimized on both sides, even as the war was being fought. That seems ethically sound to me. He was more troubled by offensive operations like the Peenemünde raid, where the explicit goal included killing scientists and engineers. They were legitimate military targets under the laws of war. They were developing weapon systems, working for the enemy military. But they were also colleagues, fellow scientists. It troubles me that the best way to stop their work was to kill them. These reflections informed Jones's teaching and shaped how he mentored students entering defense-related fields. He encouraged them to maintain ethical awareness, to question orders if they seemed morally dubious, but also to recognize that defending one's country against genuine threats was honorable work. Jones lived long, enough to see electronic warfare evolve far beyond what had been possible during World War II. By the 1990s, military forces employed extraordinarily sophisticated systems that made the beam warfare of the 1940s look almost quaint by comparison. Modern electronic warfare encompasses radar jamming, communication disruption, GPS spoofing, cyber attacks on computer networks, and directed energy weapons. The electromagnetic spectrum has become as contested as physical terrain, with advanced militaries devoting enormous resources to achieving and maintaining superiority in this domain. Jones found these developments fascinating and somewhat disturbing. He appreciated the technical sophistication but worried about implications. In 1940, we were trying to prevent bombers from accurately targeting factories. Today's electronic warfare could disable entire nations' infrastructure, electrical grids, financial systems, communications networks. The scale of potential disruption has increased by orders of magnitude. He was particularly interested in stealth technology, aircraft, and ships designed to minimize their electromagnetic signatures and avoid detection by radar. This represented a reversal of the dynamic from World War II, where improving detection was paramount. Now, avoiding detection had become equally important. "We're constantly cycling between detection and concealment," Jones observed. "Develop better radar so adversaries develop stealth. Develop better ways to detect stealth so they develop better stealth. It's an endless technological competition, exactly like what we experienced with beam systems and countermeasures." The emergence of cyber warfare in the final years of Jones's life particularly intrigued him. Attacking enemy computers to disrupt their systems or steal information represented electronic warfare taken to a new level. "It's not just interfering with signals anymore," he noted. "It's reaching into enemy systems and manipulating them directly. That's extraordinary capability and extraordinary danger." As Jones's story became more widely known through declassification, memoirs, and historical research, it inevitably became simplified and mythologized. Popular accounts tended to focus on dramatic moments while eliding complex technical details and institutional dynamics. Jones himself was ambivalent about this. He wanted the historical record to be accurate and complete, but he recognized that general audiences needed simplified narratives to engage with the story. Most people don't care about the technical details of antenna arrays or modulation schemes, he acknowledged. They want to know about the human drama, the stakes, the personalities. That's fine, as long as the fundamental truth isn't lost. Some mythologization bothered him more than others. He objected to accounts that portrayed him as a lone genius, single-handedly defeating the German threat. I had a team. I had support from senior leadership. I built on work by other scientists. Portraying me as working in isolation is simply false and does a disservice to everyone else who contributed. He was also uncomfortable with narratives that portrayed the Battle of the Beams as a clean, decisive British victory. It was messy. We had failures as well as successes. German bombers still got through and killed thousands of people. Yes, our countermeasures reduced the damage, but people still died. That's not a clean victory. It's just less catastrophic defeat than might have been. But Jones recognized the value of his story for inspiring interest in science and demonstrating the importance of scientific expertise to national security. If popularized accounts encouraged young people to pursue science and engineering careers, that was worthwhile, even if the details were simplified. In his final years, Jones cooperated with historians, journalists, and documentary filmmakers, trying to ensure that accurate accounts of the beam warfare battle were preserved and disseminated. He gave interviews, provided access to his personal papers, and reviewed manuscripts to correct errors. "This history matters," he said in a 1996 interview, the year before his death. "Not because I want to be remembered, though I'm human enough to admit that's pleasant. It matters because we need to understand how science contributes to national security, how small teams can have strategic impact, and how intelligence and innovation can counter superior numbers or resources. These lessons remain relevant. The principles Reginald Jones established in the Battle of the Beams remain foundational to modern electronic warfare and signals intelligence. Every time a military force jams enemy radar, every time an intelligence agency intercepts and decrypts communications, every time a cyber warfare team penetrates adversary networks, they're employing concepts and methods that trace directly to Jones's wartime innovations. Specific technologies have evolved beyond recognition. Modern systems operate at speeds and with sophistication that would have seemed like magic in 1940, but the underlying principles remain constant. Detect, identify adversary systems and capabilities through technical surveillance and signal monitoring. Analyze, reverse engineer system operation from fragmentary evidence, combining technical expertise with creative inference. Counter, develop precise responses tailored to exploit specific vulnerabilities in adversary systems. Adapte, tour, continuously evolve countermeasures to match adversary innovations, maintaining advantage through superior understanding and faster adaptation. These principles apply not just to military applications, but to competitive domains throughout society. Cybersecurity professionals use similar approaches to detect and counter computer intrusions. Businesses engage in competitive intelligence, trying to understand rivals' capabilities and strategies. Even scientific research often involves inferring complex systems from incomplete data, exactly the challenge. Jones faced with German beam systems. Jones's legacy extends beyond specific technical contributions to broader lessons about innovation, problem-solving, and the role of expertise in addressing complex challenges. His approach, combining rigorous technical analysis with creative insight, maintaining both confidence and humility, and accepting responsibility for the consequences of one's work, remains a model worth emulating. The invisible war that Jones fought in the 1940s never truly ended. It evolved into the Cold War's intelligence battles, then into modern counterterrorism and cyber warfare, and continues today in forms that would astound Jones but would also be immediately recognizable to him as extensions of principles he helped establish. Every nation with significant military capability now maintains electronic warfare and signals intelligence services employing thousands of scientists, engineers, and analysts. They work in facilities around the world, monitoring electromagnetic emissions, analyzing adversary systems, and developing countermeasures. They are, in a very real sense, fighting the invisible war that Jones began. Most of them probably don't know Jones's name or the details of his wartime service, but they work in a profession he helped create, using methods he pioneered, pursuing goals he first articulated. His legacy isn't primarily in the specific technologies he developed. Those became obsolete decades ago, but in the approach to scientific intelligence and electronic warfare that he established, and that continues guiding the field today. In a quiet cemetery in Aberdeen, Scotland, a simple headstone marks Reginald Jones's grave. It bears his name, dates, and a brief phrase, scientist and patriot. It's a modest memorial for a man whose contributions were anything but modest. His invisible war saved thousands of lives, helped secure Britain's survival, and pioneered entirely new approaches to intelligence and warfare that continue shaping our world today. He proved that one person with knowledge, creativity, and determination could change the course of history. He demonstrated that science applied to defense isn't about building bigger bombs, but about understanding adversaries more deeply than they understand themselves. And perhaps most importantly, he showed that the impossible is often just the difficult in disguise, waiting for someone with enough insight and persistence to reveal its secrets. The invisible weapons that were supposed to bring Britain to its knees instead exposed Germany's technological vulnerabilities, thanks to a young physicist who refused to believe that radio beams were impossible and who dedicated himself to seeing what others could not. That may be Reginald Jones's greatest legacy. Not any specific technical achievement, but the demonstration that curiosity, rigor, and courage can triumph over any threat, no matter how invisible or intimidating it may seem. The war he fought was invisible. The weapons he created were invisible. Even his contributions remained invisible for decades after the war ended. But the impact was anything but invisible. It shaped history. It saved a nation. And it continues resonating through every invisible battlefield where the wars of the 21st century are being fought.